Time feels like the most reliable thing in the world. It passes the same way for everyone. At least, that is what every person assumed for nearly all of human history. A second was a second. An hour was an hour. Whether you stood on a mountaintop or sat in a valley, whether you raced across the land or stayed perfectly still, time was thought to flow forward at one fixed and universal rate. The clock in your home and a clock thousands of miles away kept the same perfect rhythm. Nobody needed to prove this. It was woven so tightly into ordinary experience that doubting it would have seemed absurd. That assumption turned out to be wrong. Not slightly wrong, but wrong at its very foundation. And the person who exposed the error changed our understanding of reality forever. Albert Einstein had no great laboratory at his disposal. He owned no observatory, ran no costly experiments, and commanded no team of researchers. The instrument he relied on most was his own mind. With it, he showed that time bends and stretches in ways that defy every instinct we have. Time slows when you move quickly through space. It runs more slowly near massive objects like planets and stars. Two people, depending on how they move, can disagree about whether two events happened at the same moment, and both of them can be right. A clock flown aboard a fast aircraft genuinely returns having lost a fraction of a second compared to the clock left behind on the ground. None of this is guesswork. It has been measured directly, confirmed by instruments accurate enough to remove all doubt. These effects are not locked away in some distant region of the universe. They reach into daily life, shaping the satellites that guide your travels and the very structure of the cosmos. This is the story of how a single person took apart humanity's oldest assumption about reality and what we discovered hidden beneath it. To understand how radical Einstein's ideas were, you have to first understand the world he inherited, a world built almost entirely on the foundation laid by Isaac Newton more than 2 centuries earlier. Newton had given humanity something extraordinary. He had taken the apparent chaos of the heavens and the messy unpredictability of motion on Earth and shown that both obeyed the same precise mathematical laws. A falling apple and an orbiting moon followed identical principles. The same equations that described a cannonball arcing across a battlefield also described planets sweeping around the sun. It was one of the greatest intellectual achievements in human history, and at the heart of it sat a particular vision of time and space. In Newton's universe, time was absolute. It flowed, in his own description, equably and without relation to anything external. Picture a single immense clock, located nowhere in particular and everywhere at once, ticking away the seconds for the entire cosmos. Every event, no matter where it occurred, could in principle be stamped with a moment on that universal clock. When a star exploded in a distant galaxy and when a candle flickered in a quiet room, both happened at definite instants measured against the same eternal flow. Time was the stage. The universe was the play performed upon it. The stage itself never moved, never warped, never cared what happened on its surface. Space worked the same way. It was a vast, empty, motionless container stretching infinitely in all directions, indifferent to whatever it held. You could imagine an invisible grid laid across all of existence, a fixed framework of length, width, and height against which every position could be precisely defined. A meter was a meter everywhere. Distance was distance, fixed and dependable. Space provided the room in which things existed, and time provided the sequence in which they changed, and the two were entirely separate. One had nothing to do with the other. You could no more mix space and time than you could mix temperature and color. This picture was not merely accepted by scientists. It matched human intuition so perfectly that it felt less like a theory and more like plain common sense. Everything in ordinary experience confirmed it. When you arrange to meet someone at a particular hour, you assume your watch and theirs are measuring the same time. When two events happen, you assume there is always a definite fact about which came first, or whether they happened together. If a window breaks and a sound is heard, surely the entire universe agrees on the order in which those things occurred. Newton's framework took these everyday certainties and elevated them into the bedrock of physics. For 200 years, it held without serious challenge, and it held for good reason. It worked. It predicted the motions of the planets with stunning accuracy. It guided the construction of machines, the design of bridges, the calculations of astronomers. When a new planet, Neptune, was discovered in the 1800s, it was found because Newton's laws predicted exactly where an unseen world had to be, tugging on the orbit of its neighbor. Few theories in the history of science have ever earned such overwhelming confidence. And yet, beneath this triumphant structure, small troubles were beginning to stir. They were not obvious, and for a long time they seemed like minor technical puzzles rather than cracks in the foundation. The trouble centered on light. Throughout the 1800s, physicists had been steadily uncovering the nature of light, and what they found was that light behaved as a wave. It rippled and interfered and bent around obstacles in exactly the way waves do. But this raised an immediate and nagging question. Every wave that anyone had ever studied was a disturbance traveling through some medium. Sound waves traveled through air. Ocean waves traveled through water. Vibrations traveled through solid materials. A wave was, by its very nature, a moving pattern in some substance. So if light was a wave, what was the substance it moved through? What was waving? Scientists proposed an answer. They imagined that all of space, even the seemingly empty void between the stars, was filled with an invisible, weightless, frictionless substance they called the luminiferous ether. This ether was supposed to be the medium that carried light, the cosmic ocean in which light waves rippled. It had to be strange almost beyond imagining. It had to fill every corner of the universe, pass through solid objects without resistance, and yet be rigid enough to carry waves traveling at the immense speed of light. But however strange it seemed, the ether solved the problem on paper, and it preserved Newton's tidy framework. Light, like everything else, moved through a fixed medium sitting motionless in absolute space. This idea carried a clear and testable consequence. If the ether truly filled space and sat still, then the Earth, hurtling around the sun, must be moving through it. There should be a kind of cosmic wind, an ether wind, blowing past our planet as it races along its orbit, much as you feel a breeze on your face when you stick your hand out of a moving car window. And if light traveled through the ether, then its measured speed should depend on the direction you measured it. Light moving in the same direction as the ether wind should travel at a slightly different speed than light moving against it or across it. The difference would be tiny, but with careful enough instruments, it should be detectable. Finding it would confirm the existence of the ether and reveal Earth's true motion through absolute space. It seemed like a straightforward task, the kind of careful measurement that 19th century physics excelled at. In the 1880s, two American scientists, Albert Michelson and Edward Morley, set out to detect this ether wind with an instrument of remarkable precision. They built a device that split a beam of light into two parts, sent those parts racing along two paths set at right angles to each other, and then recombined them. If the two beams traveled at even slightly different speeds because of the ether wind, the recombined light would show a telltale pattern, a shift in the bands of light and dark that the instrument produced. The apparatus was sensitive enough to detect differences far smaller than anyone expected the effect to be. They floated it on a pool of liquid mercury so they could rotate it smoothly and check the light's behavior in every direction. They were confident. The experiment was sound. The reasoning was impeccable. The result was nothing. No shift, no difference. No matter which way they turned the instrument, no matter what time of day or what season of the year, the two beams of light always returned in perfect step. The ether wind that should have been there simply was not. Light traveled at exactly the same speed in every direction, as though the Earth were not moving through any medium at all. It was one of the most famous failed experiments in the history of science, and its failure was profound. The measurement had been done with exquisite care, and it had returned a result that made no sense within the accepted picture of reality. For years, physicists struggled to explain it. Some suggested the Earth might drag the nearby ether along with it, carrying it like a bubble of still air. Others proposed that objects moving through the ether physically contracted in the direction of motion by just the right amount to hide the effect. A strange and almost desperate idea that patched the equations without explaining why such a thing should happen. These were clever fixes, but they had the feeling of repairs made to a structure that was quietly failing. Each new patch saved the appearances for a while, yet none of them touched the deeper problem. Something was wrong at the foundation, and the more carefully physicists looked, the more the old certainties seemed to wobble. This was the situation as the new century opened. The grand edifice of Newtonian physics still stood, magnificent and successful, accurately predicting the motions of planets and the trajectories of projectiles. But at its base, in the behavior of light, sat a stubborn fact that refused to fit. The speed of light would not cooperate. It ignored the motion of the Earth. It ignored the direction of measurement. It simply was what it was, unchanging and absolute, in a universe where the old rules said its speed should depend on how the observer moved. Most physicists assumed that some clever adjustment, some new wrinkle in the theory of the ether, would eventually resolve the difficulty and restore order. They could not yet imagine that the problem was far deeper than any adjustment could reach, that resolving it would require tearing down the very idea of absolute time and absolute space that Newton had built his universe upon. What they needed was not another patch. They needed someone willing to take the strange behavior of light not as a problem to be explained away, but as a clue pointing toward a different reality altogether. And that person was, at that very moment, working in obscurity far from any university, examining patent applications at a government office in Switzerland. The man who would resolve the crisis was, in the early 1900s, not a famous professor or a celebrated researcher. He was a junior clerk in a patent office in the city of Bern, Switzerland, evaluating applications for inventions, many of them devices for measuring and coordinating time. There is a quiet irony in this. The young Albert Einstein spent his working days surrounded by blueprints for clocks and schemes for synchronizing the timepieces of distant railway stations, never imagining that these mundane concerns would echo through the deepest work of his life. He had not landed in this position by choice. He had wanted an academic post, a place at a university where he could research and teach. But despite his evident brilliance, he had struggled to find one. His professors had found him difficult, a student who questioned too much and deferred too little. So he took the patent job to pay his rent, and in the hours left over, he thought about physics. This detail matters more than it might first appear. Einstein was working outside the established institutions of science. He had no senior colleagues looking over his shoulder, no laboratory directing his attention toward fashionable problems, no career pressure pushing him toward safe and incremental work. He was free in a way few scientists ever are, free to follow his own curiosity wherever it led, and free to question assumptions that better-positioned scientists took for granted. The patent office, far from being a prison for his talents, may have been exactly the environment he needed. It gave him a steady income, undemanding work that left his mind unoccupied, and the solitude to think long and hard about the questions that fascinated him. He would later look back on these years with something close to fondness, calling the patent office a kind of worldly monastery where he hatched his most beautiful ideas. And the question that fascinated him most was one he had been turning over since he was a teenager. As a boy of 16, Einstein had asked himself what would happen if he could chase a beam of light and catch up to it. If light was a wave traveling through space and he could somehow ride alongside it at the same speed, what would he see? By the ordinary logic of motion, the answer seemed clear. Just as a person running alongside a train sees the train standing still relative to them, a person traveling alongside a light wave should see the wave frozen in place, a stationary pattern of electric and magnetic fields hanging motionless in space. But this answer troubled him deeply. The equations that governed light, worked out by the physicist James Clerk Maxwell, did not allow for such a thing. According to those equations, light was always in motion. A frozen light wave was not a solution the laws of physics permitted. There was no such thing as a stationary beam of light. The very idea was a contradiction. Here was a young man sensing, long before he could prove it, that something was deeply strange about light and motion and the relationship between them. The ordinary rules of how speeds add together, rules that everyone accepted without a second thought, seem to break down when applied to light. Consider how velocities normally combine. If you walk forward through a moving train at a few kilometers per hour, and the train moves along the tracks at a much greater speed. Then a person standing beside the tracks sees you moving at the sum of the two speeds, your walking pace added to the train's motion. This is the most natural thing in the world. Speeds add. Throw a ball forward from a moving vehicle, and the ball travels faster relative to the ground than it would if you threw it standing still. Everything in everyday experience obeys this simple arithmetic of motion. But light refused to play by these rules, and the Michelson and Morley experiment had shown it. The speed of light did not add to or subtract from the motion of its source or the motion of the observer. It stubbornly remained the same. Einstein took this fact, which had so confounded the physicists of his day, and did something that required a peculiar kind of courage. Instead of treating the constant speed of light as a problem to be explained away with elaborate fixes about the ether, he decided to accept it as a fundamental truth about the universe. He would assume as a starting principle that the speed of light is the same for every observer, no matter how that observer is moving. And then he would follow the logic wherever it led, no matter how strange the destination. This was the move that separated Einstein from his contemporaries. Other physicists had the same facts in front of them. They had the failed ether experiments, the troublesome equations, the stubborn constancy of light speed. But they kept trying to force these facts back into the familiar framework of absolute space and absolute time. They could not bring themselves to abandon the comfortable certainties of Newton's universe. Einstein was willing to do exactly that. He grasped that you could not hold on to both the constancy of light and the old idea of absolute time. One of them had to go. And since the constancy of light was what the experiments actually showed, it was absolute time that would have to be sacrificed. In the year 1905, working in his spare hours with no laboratory and no collaborators, Einstein produced a series of papers that would transform physics. This single year became known as his miracle year because the output was so concentrated and so revolutionary. One paper explained the photoelectric effect, treating light as packets of energy and helping to launch the quantum revolution, work that would later earn him the Nobel Prize. Another explained the jittery motion of tiny particles suspended in fluid, providing some of the strongest evidence yet that atoms were real. But the paper that concerns this story carried a modest and almost dull title, something about the electrodynamics of moving bodies. Within it lay the theory that would come to be called special relativity, and it dismantled the Newtonian picture of time. What makes the achievement so remarkable is how Einstein built it. He did not begin with new experimental data gathered from some clever apparatus. He began with principles and reasoning, with thought experiments performed entirely in his imagination. He pictured trains and lightning bolts, moving observers and beams of light, and he reasoned about what each observer would necessarily see if the speed of light truly was constant for all of them. This method, thinking through a physical situation in careful detail to expose its hidden logic, became one of his signatures. He could not chase a beam of light in reality, but he could chase it in his mind. And by doing so, he uncovered truths that no laboratory of his era could have revealed. The foundation of the whole theory rested on just two simple statements, two principles from which everything else would flow. The first was the principle of relativity itself, an idea that actually predated Einstein and went back to Galileo. It states that the laws of physics are the same for all observers moving at constant velocity. There is no special privileged state of rest in the universe. If you are inside a smoothly moving vehicle with no windows, no bumps, and no sound from outside, there is no experiment you can perform within it to determine whether you are moving or standing still. Pour a drink, toss a ball, watch it fall, and everything behaves exactly as it would if the vehicle were parked. Motion at a steady speed in a straight line is, in a deep sense, indistinguishable from rest. There is no absolute standard against which to measure who is really moving. All such motion is relative, defined only in comparison to something else. The second principle was the radical one, the one Einstein had wrestled from the behavior of light. The speed of light in empty space is the same for all observers, regardless of the motion of the light source or the observer. This was the fact the experiments demanded and the equations of Maxwell required, and Einstein simply took it as bedrock. No matter how fast you move toward a beam of light or away from it, you will always measure that light traveling at the same fixed speed. You cannot catch up to light. You cannot make it appear to slow down by chasing it or speed up by fleeing from it. Its speed is woven into the structure of the universe itself, an absolute limit and an absolute constant. These two principles seem innocent enough on their own. The first feels almost obvious, a statement about the democracy of motion. The second sounds like a peculiar but isolated fact about light. But Einstein saw that when you hold both of them to be true at the same time, something has to give. And what gives is the thing nobody expected. If the laws of physics are the same for everyone, and if the speed of light is the same for everyone, then time and space themselves cannot be the same for everyone. They must bend and stretch and shift to keep the speed of light constant. Absolute time, the universal clock ticking the same for all, becomes impossible. The two innocent principles, taken together, lead by unavoidable logic to the unraveling of time as everyone had understood it. To see exactly how this unraveling happens, we have to follow Einstein into one of his thought experiments, and there is no better place to begin than with a train, a pair of lightning strikes, and a simple question about whether two things happen at the same moment. Picture a long train moving down a straight track at tremendous speed, and imagine that lightning strikes it twice, once at the very front of the train and once at the very rear. The two bolts strike at the same instant, leaving scorch marks on both the train and the ground beside it. Now place two observers in this scene. One stands on the embankment beside the tracks, positioned exactly halfway between the 2 points where the lightning struck the ground. The other rides inside the train, seated precisely at its midpoint, halfway between the front and rear. The question Einstein asked was deceptively simple. Did the two lightning bolts strike at the same time? And the answer he uncovered shattered the idea of a universal present moment. Consider first the observer standing on the embankment. The light from each lightning strike races toward this person from opposite directions, from the front strike and the rear strike. Because this observer stands exactly midway between the 2 points, and because light travels at a fixed speed, the light from both strikes covers the same distance and arrives at the same moment. This observer sees the two flashes simultaneously and concludes, quite reasonably, that the two bolts struck at the same time. For the person on the ground, the events were simultaneous. There is nothing controversial about this. It matches every intuition we have. Now consider the observer seated at the middle of the moving train. Here is where the trouble begins. At the instant the lightning strikes, this observer happens to be located at the midpoint of the train, lined up with the observer on the ground. But the train is moving, and moving fast. During the brief time it takes for the light from each strike to travel toward the center of the train carries its passenger forward, toward the front of the train and away from the rear. This means the observer on the train is moving toward the light coming from the front strike and away from the light coming from the rear strike. The light from the front therefore has a shorter distance to cover before it reaches this observer, while the light from the rear has farther to go. Here is the crucial point, the place where the constancy of light becomes decisive. The speed of light is the same for the observer on the train as for the observer on the ground. Light does not travel faster just because the train moves toward it. So the observer on the train cannot say that the light from the front simply sped up to compensate. The light from both strikes travels at exactly the same speed for this observer as well. And since the light from the front had less distance to cover, and the light from the rear had more, the light from the front arrives first. The observer on the train sees the front lightning strike before the rear lightning strike. For this person, the two events were not simultaneous at all. The front bolt clearly struck before the rear bolt. Stop and absorb what has just happened. The observer on the ground says the two strikes were simultaneous. The observer on the train says the front strike happened first. These are not differing opinions about the same reality, where one is right and the other is mistaken. Neither observer has made an error. Neither has a faulty clock or a poor vantage point. Both have reasoned correctly from what they actually saw, and both are entirely correct within their own frame of reference. The simultaneity of the two events, whether they happened at the same time or not, depends on who is asking. There is no single true answer that applies to everyone. The question whether two separated events happen at the same time has no universal answer. This idea is called the relativity of simultaneity, and it is one of the most quietly profound conclusions in all of physics. It strikes directly at the heart of the Newtonian universe. In Newton's picture, there was always a definite fact about whether two events happened at the same moment, because there was a universal time stamping every event with a single, agreed-upon instant. Einstein has just shown that no such universal time exists. The notion of now, of a present moment shared by the entire universe, simply dissolves. Your now and the now of someone moving relative to you are genuinely different. Events that you consider simultaneous, they may consider to happen in sequence, and events they consider simultaneous, you may split apart in time. There is no master clock that settles the matter, because there is no master clock at all. It is worth pausing to address the natural objection that rises up at this point. Surely, one wants to say, the events really did happen at the same time, or they really did not. Surely there is a fact of the matter, even if different observers, fooled by the travel time of light, disagree about it. But this objection misunderstands what relativity is claiming. It is not saying that the observers are deceived by some illusion, that beneath the appearances there is still a true ordering they have failed to perceive. It is saying that there is no such true ordering. Simultaneity is not a property of events themselves. It is a relationship between events and an observer, and it changes when the observer changes. The travel time of light is not a distortion hiding the truth. It is the very thing that defines what simultaneity means, and since the speed of light is the same for everyone while their states of motion differ, their judgments of simultaneity must differ too. There is no deeper fact being missed. The disagreement is the reality. This single insight is the thread that, once pulled, unravels the entire fabric of absolute time. If observers cannot agree on whether two events are simultaneous, then they cannot agree on a universal ordering of events, and if they cannot agree on the ordering of events, then time itself cannot be the single flowing river that Newton imagined, carrying all of existence forward at one shared rate. Each observer carries their own sense of time, their own slicing of the universe into past, present, and future. And these slices do not line up. What is present for one is, for another, already part of the past or still waiting in the future. Time has become personal, tied to the observer's motion, rather than universal and absolute. And the strangeness does not stop at simultaneity. Once you accept that the speed of light is constant for all observers, a whole cascade of consequences follows, each one stranger than the last, and each one forced upon us by the same relentless logic. If light always travels at the same speed for everyone, and yet different observers measure different distances and different timings for the same events, then the very measurements of distance and time must themselves be flexible. Space and time must adjust to preserve the one quantity that nature insists on holding fixed, the speed of light. This is the key to understanding everything that follows. Whenever the constancy of light seems to lead to a contradiction, the resolution is always the same. Space stretches or shrinks, and time speeds up or slows down by exactly the amount needed to keep light speed unchanged for every observer. Time and space bend so that light can stay constant. To see how this works in the case of time, imagine a particularly clean kind of clock, one stripped down to its barest essentials. Picture a clock made of two mirrors facing each other, one above the other, with a single pulse of light bouncing between them. Each time the light pulse completes a round trip up to the top mirror and back down to the bottom, the clock ticks once. This is sometimes called a light clock, and it is a wonderfully simple device for thinking about time, because its ticking is governed entirely by the speed of light and the distance between the mirrors. Since the speed of light is constant, such a clock keeps perfectly regular time. The light goes up, comes down, and that round trip defines one tick. Nothing could be more straightforward as long as the clock sits still. Now, set this light clock in motion. Imagine it mounted inside a vehicle moving rapidly past you while the light pulse continues to bounce between its mirrors. For someone riding alongside the clock, traveling with it, nothing has changed. The light still goes straight up and straight down, and the clock ticks at its normal rate. But for you, standing still and watching the clock fly past, something different happens. As the light travels from the bottom mirror to the top, the entire clock moves forward, so by the time the light reaches the top mirror, that mirror has shifted ahead. The light cannot travel straight up as seen from your vantage point. It must travel diagonally, following the moving mirror, tracing out a slanted path. And on the way back down, it again moves diagonally as the clock continues forward. From your point of view, the light pulse traces a long zigzag, a series of diagonal lines rather than a simple vertical bounce. Here is the decisive consequence. A diagonal path is longer than a straight vertical path. The light, as you observe it, has to travel a greater distance to complete each round trip. But the speed of light is constant. It cannot travel that longer diagonal path any faster than it would travel the short vertical one. And if light must cover a greater distance at the same unchanging speed, then it must take more time to do so. From your perspective, each tick of the moving clock takes longer than each tick of an identical clock sitting still beside you. The moving clock runs slow. Time, as measured by that moving clock, has genuinely stretched out. This effect is called time dilation, and it is not an illusion or a trick of perception. It is a real consequence of the constancy of light, forced upon us by the same logic that gave us the relativity of simultaneity. A clock in motion ticks more slowly than a clock at rest, and the faster it moves, the more pronounced the slowing becomes. The question that immediately arises is just how much slower a moving clock runs, and whether this strange effect could ever grow large enough for anyone to actually notice it. The amount by which a moving clock slows depends entirely on its speed, and for the speeds of ordinary life, the effect is so tiny that it escapes all notice. This is precisely why no one ever stumbled upon time dilation in everyday experience, and why the Newtonian picture survived unchallenged for so long. A car racing down a highway, an aircraft crossing a continent, even a spacecraft escaping the pull of the Earth, all move at speeds that are minuscule compared to the speed of light. Light travels at roughly 300,000 kilometers every second, a velocity so enormous that the fastest machines humanity has ever built crawl along by comparison. At these modest speeds, the slowing of time amounts to fractions of a second, far too small for any human being to feel, and far too small for ordinary clocks to register. Time dilation was always present, woven into the structure of reality, but it remained hidden because we never moved fast enough to see it. The effect only becomes dramatic as you approach the speed of light. As a clock's speed climbs toward that ultimate limit, the slowing of time grows steeper and steeper, eventually rising without bound. At a small fraction of light speed, the effect is barely perceptible. At half the speed of light, a moving clock runs noticeably slow, ticking at roughly 7/8 the rate of a stationary one. At 90% of light speed, the moving clock falls to less than half the normal rate. Push closer still to 99% of light speed, and the moving clock slows to about 1/7 the rate of a clock at rest. And as the speed creeps ever nearer to that of light, the slowing becomes extreme without limit. A clock moving at 99.99% of light speed would tick so slowly that what feels like a single year aboard it would correspond to many decades for those left behind. The closer you press toward the speed of light, the more violently time stretches, until at the speed of light itself, time, in a sense, would stop altogether. This is one reason nothing with mass can ever quite reach that speed, but that is a thread to follow later. What makes this more than a mathematical curiosity is that it has been measured directly with real clocks in real experiments. The behavior of moving clocks is not a philosophical speculation that lives only in thought experiments. It is a confirmed feature of the physical world, demonstrated again and again with growing precision. One of the most elegant confirmations came not from any human-built clock, but from nature itself in the form of tiny particles raining down from the upper atmosphere. High above the Earth, cosmic rays from space slam into the air and produce showers of particles, among them a kind of particle called a muon. Muons are unstable. Once created, they survive for only a tiny sliver of time before they decay and vanish, transforming into other particles. Their lifespan is so brief, measured in millionths of a second, that even traveling at nearly the speed of light, they should decay long before reaching the ground. By the ordinary reckoning, the vast majority of them ought to disappear high in the atmosphere, with almost none surviving the journey down to the surface. And yet, detectors at the surface of the Earth find muons arriving in great numbers, far more than should be possible if their lifespans were what they are when measured at rest. The explanation is time dilation. The muons are moving so fast, so close to the speed of light, that from our perspective on the ground, their internal clocks run slow. The brief moment of life allotted to a muon stretches out, as measured by us, into a much longer span, long enough for the particle to complete its plunge through the atmosphere and reach our detectors before decaying. The muons are living longer than they should, not because anything has changed about the muons themselves, but because time is passing more slowly for them relative to us. Every shower of muons reaching the ground is a quiet confirmation that Einstein was right, a natural experiment running continuously, day and night, all across the surface of the planet. There is an elegant symmetry in how the muon experiences this same situation, and it reveals something important about the theory. From the muon's own point of view, its lifespan is perfectly normal. It does not feel its time running slow, because from its own frame of reference, it is the one at rest, and the Earth is rushing up to meet it at nearly the speed of light. So how does the muon reach the ground within its short lifetime? For the muon, the answer is not that time has stretched, but that distance has shrunk. The thickness of the atmosphere, which we measure as many kilometers, is for the fast-moving muon compressed to a much shorter distance. This is the companion effect to time dilation, known as length contraction. Just as moving clocks run slow, moving objects shrink along their direction of motion. The muon does not need extra time to cross the atmosphere, because for the muon, the atmosphere is thin. Both observers, the muon and the scientist on the ground, agree that the muon reaches the surface. They simply explain it differently, one through stretched time and the other through contracted space. The reality they share is preserved, even as their measurements of time and distance disagree. The same effects have been confirmed with actual clocks carried aboard aircraft. In a famous experiment, extremely precise atomic clocks were loaded onto airplanes and flown around the world, while identical clocks remained behind on the ground. When the traveling clocks returned and were compared with their stationary counterparts, they had fallen behind by exactly the amount Einstein's equations predicted, billionths of a second, but billionths that matched the prediction with remarkable accuracy. The flying clocks had genuinely experienced less time than the ones left on the ground. This was not a measurement error, not a quirk of the instruments. It was time dilation made tangible, demonstrated with the kind of clocks that keep time so steadily they lose less than a second over millions of years. The experiment has been repeated and refined many times, always with the same result. Move a clock and it falls behind. Time is not absolute. It depends on motion, exactly as the theory demands. Modern particle accelerators provide an even more extreme and routine confirmation. In these machines, physicists accelerate particles to within a hair's breadth of the speed of light, and they observe the lifetimes of unstable particles stretching out by enormous factors. A particle that would decay almost instantly at rest can be made to survive far longer, simply by setting it in rapid motion. The faster the particle moves, the longer it lives, and the amount of extra life it gains matches Einstein's predictions precisely. These effects are so reliable, so thoroughly built into the daily operation of such machines, that engineers must account for them as a matter of routine. Time dilation is not an exotic possibility to be tested now and then. It is an everyday engineering fact, as ordinary to the physicists who work with these machines as friction or gravity is to the rest of us. All of this forces a profound reconsideration of what time actually is. We are accustomed to thinking of time as a fixed background, the same for everyone, a universal current carrying all of existence forward together. But the evidence says otherwise. Time is local. It belongs to each moving thing individually. Your time and the time of a fast-moving particle, or a clock on an airplane, or a muon falling from the sky, are not the same time. Each follows its own clock, and those clocks tick at different rates depending on how they move. There is no master rhythm to which all of nature keeps step. There are only the individual rhythms of individual things, drifting in and out of agreement as their motions change. The universal clock of Newton has been quietly retired, replaced by a vast multitude of private clocks, each keeping its own faithful time. This raises a question that sounds at first like a paradox, and which troubled even careful thinkers when relativity was new. If motion is relative, if there is no privileged state of rest, then each observer can claim to be the one standing still while the other moves. The muon sees the earth rushing toward it just as surely as the earth sees the muon rushing down. The clock on the airplane could, in principle, regard itself as motionless while the ground races beneath it. So if each can consider the other to be the one in motion, then each should see the other's clock running slow. And indeed, that is exactly what happens. Each observer, with equal justification, sees the other's clock ticking more slowly than their own. This seems to lead straight into contradiction. How can each clock be slower than the other? Surely they cannot both be running behind. If we ever brought the two clocks back together and compared them side by side, one of them would have to show less time than the other, and they could not both be the one that fell behind. The resolution of this puzzle takes us to one of the most famous scenarios in all of physics, a tale of two siblings, one who journeys to the stars and one who stays home, and the startling difference in their ages when they finally meet again. The scenario is usually told with twins, two siblings of identical age, because twins make the comparison vivid. One twin boards a spacecraft and travels to a distant star at a speed close to that of light, then turns around and comes home. The other twin remains on Earth, living an ordinary life, watching the years pass. When the traveling twin returns and the two are reunited, they are no longer the same age. The twin who journeyed to the stars has aged less than the twin who stayed behind. If the speed and distance are great enough, the difference can be enormous. The traveler might return after what feels to them like a few years away, only to find that decades have elapsed on Earth, that the sibling they left behind has grown old, that the world they knew has moved on without them. This is the famous twin scenario, sometimes called the twin paradox, and it is not a fantasy. It is a direct and unavoidable consequence of time dilation, and a version of it has been confirmed by experiment. But the scenario is called a paradox for a reason, and the apparent contradiction is exactly the one raised at the end of our discussion of moving clocks. If all motion is relative, then from the traveling twin's point of view, it is the Earth and the stay-at-home twin that go racing away and then return. The traveler could just as well consider themselves to be at rest, with the rest of the universe doing the moving. And if that is so, then by the same logic of time dilation, the traveler should expect the earthbound twin's clock to run slow, meaning the stay-at-home twin should end up younger, not older. Each twin, applying the principle of relativity, seems entitled to conclude that the other should be the younger one when they reunite. They cannot both be right. When they finally stand face to face, one of them really will be older, and the matter will be settled by simple observation. So which twin ages less, and why does the symmetry between them break? The resolution lies in recognizing that the two twins are not, in fact, in symmetric situations. They are not interchangeable. There is a real physical difference between what the two of them experience, and that difference is the key to the whole puzzle. The twin who stays on Earth remains in a single, unchanging state of motion throughout the entire episode. This twin never speeds up, never slows down, never changes direction. They simply coast along in what physicists call a single inertial frame from start to finish. The traveling twin, by contrast, does something the stay-at-home twin never does. The traveler accelerates. They fire their engines to leave the Earth, build up to tremendous speed, and then, crucially, at the distant star, they must turn around. To come home, they have to decelerate, stop, reverse direction, and accelerate back toward Earth. This turnaround involves a real physical change in motion, a force that the traveling twin actually feels, pressing them into their seat, while the stay-at-home twin feels nothing of the kind. This breaks the symmetry completely. The principle of relativity, which says that all states of motion are equivalent, applies only to motion at constant velocity, to observers coasting steadily in a straight line. It does not apply to accelerated motion. Acceleration is absolute in a way that constant velocity is not. You can always tell when you're accelerating because you feel it. When a vehicle suddenly speeds up, you are pushed back. When it brakes, you lurch forward. When it rounds a curve, you are thrown to the side. These sensations are real and unambiguous, and they have no counterpart for someone moving at a steady velocity. The traveling twin feels the forces of acceleration at launch, at the turnaround, and at the return. The stay-at-home twin feels nothing. The two are simply not in equivalent situations, and so there is no contradiction in their aging differently. The traveler is the one who undergoes the genuine, felt changes in motion, and the traveler is the one who returns younger. It can help to think about why the turnaround in particular matters so much. While the traveler is coasting away from Earth at constant speed, each twin does indeed see the other's clock running slow, and the situation is symmetric during that phase. The same is true during the coasting return. The asymmetry enters at the moment of turnaround when the traveler switches from moving away to moving back. During that switch, from the traveler's perspective, something dramatic happens to their sense of what is happening now on Earth. Because of the relativity of simultaneity, the traveler's notion of which moment on Earth counts as the present jumps forward enormously during the turnaround. As the traveler reverses direction, their plane of simultaneity, the slice of the universe they regard as the present moment, sweeps rapidly across the Earth's history. A large span of time on Earth, which the travelers skipped over during the outbound trip, suddenly falls into their past as they turn around. When all the bookkeeping is done, both twins agree completely. The traveler has aged less, the stay-at-home twin has aged more. There is no contradiction, only a careful accounting of how each twin's experience of time unfolded. The deeper way to understand the twin scenario, and perhaps the most illuminating, involves a shift in how we picture motion through the universe. Imagine that every object is always moving through a combined fabric of space and time at a single fixed rate, and that this rate is, in fact, the speed of light. This sounds strange at first, but it captures something profound. An object sitting still in space is nonetheless moving through time, aging steadily, traveling into the future at the full speed allotted to it. All of its motion is directed through time, none through space. Now, set that object moving through space. To do so, some of its motion must be diverted away from the time direction and redirected into the space direction. The faster it moves through space, the less of its motion remains available for traveling through time, and so the slower it ages. Motion through space comes at the cost of motion through time. There is a fixed budget, and what you spend on moving through space, you cannot spend on moving through time. This picture makes the twin scenario almost intuitive. The stay-at-home twin devotes nearly all of their motion to traveling through time, moving very little through space, and so ages at the full rate. The traveling twin diverts a large portion of their motion into rushing through space at high speed, leaving less for the journey through time, and so ages more slowly. When the traveler returns and their two paths are compared, the traveler has simply spent less of their total motion on aging and more on covering distance. The difference in their ages is the natural result of how each divided their fixed allotment of motion between space and time. The stay-at-home twin took the long way through time. The traveler took a shortcut, but paid for it by experiencing less time along the way. This way of thinking points toward the most important conceptual leap in all of relativity, one that goes beyond any single effect like time dilation or length contraction. It suggests that space and time are not the separate, independent things that Newton imagined, with space as the container and time as the universal flow. Instead, they are bound together, two aspects of a single underlying entity. The reason moving through space affects your passage through time is that space and time are woven from the same cloth. They trade off against each other precisely because they are not truly distinct. This unification of space and time into a single fabric was not, in fact, first emphasized by Einstein himself. It was one of his former teachers, the mathematician Hermann Minkowski, who recognized the deep geometric structure hidden within Einstein's theory and gave it its proper form. Minkowski declared that henceforth space by itself and time by itself were doomed to fade into mere shadows, and that only a union of the two would preserve any independent reality. What Minkowski meant was that the true arena of physics is neither space alone nor time alone, but a four-dimensional combination of the two, a structure now called space-time. In this view, the disagreements between observers about lengths and durations are not signs of confusion or error. They are like the disagreements between two people describing the same object from different angles. One person, looking at a long thin rod held at a slant, might describe it as mostly tall with a little width. Another, viewing the same rod from a different position, might describe it as mostly wide with a little height. Both are describing the same object, but they slice it differently into the categories of height and width because they view it from different perspectives. In just the same way, different observers slice space-time differently into space and time. What one observer calls a stretch of pure time, another might call a mixture of time and space. The underlying space-time is the same for all of them. Only their slicing of it into separate space and separate time differs according to how they move. To truly understand what Einstein revealed about time, we have to follow Minkowski's insight and look closely at this single fabric of space-time, where space and time lose their separate identities and merge into something new. To grasp what space-time really is, it helps to start with how we ordinarily locate an event in the world. Suppose you want to tell someone where and when to meet you. You might give them a place specified by its position and a time specified by the clock. The place itself requires 3 numbers to pin down completely. You need to say how far east or west, how far north or south, and how far up or down. These 3 numbers, 3 independent directions, are what we mean when we say space has 3 dimensions. A point in a room can be located by its distance along the floor in 2 directions and its height above the floor in the 3rd. Any location whatsoever can be captured by these 3 measurements, but a location alone is not enough to specify an event because the same place exists at every moment. To say not just where, but when, you must add a 4th number, the time. An event, something that happens at a particular place in a particular moment, requires 4 numbers in total to specify completely. 3 for space, 1 for time. This is the simple sense in which we live in a 4-dimensional world. Before Einstein, no one thought there was anything deep about combining these 4 numbers. Space was space, with its 3 dimensions, and time was time, standing entirely apart. You needed both to specify an event, but they were regarded as utterly different kinds of things, like needing both a person's name and their weight to describe them fully, without anyone suggesting that name and weight were aspects of some single underlying quantity. What Einstein's theory revealed, and what Minkowski made precise, is that space and time are not separate in this way. They are interwoven dimensions of a single 4-dimensional structure, and the way they combine is governed by definite rules. This 4-dimensional structure is space-time, and every event in the history of the universe is a single point within it, marked by its 3 spatial coordinates and its 1 temporal coordinate. The entire history of any object, every place it has ever been at every moment of its existence, traces out a continuous line through space-time, a path that physicists call its world line. Think of your own world line. At this moment, you occupy a particular point in space and a particular point in time. A moment from now, you will occupy a slightly different point in time and perhaps a slightly different point in space if you have moved. Stringing all these points together, from your birth to the present and onward to the end of your life, produces an unbroken curve threading through the 4-dimensional fabric of space-time. Everything that exists has such a world line. A planet orbiting its star traces a long helix through space-time, spiraling forward in time as it circles in space. A photon of light traces a straight path. A rock sitting motionless on the ground still traces a world line, moving steadily forward through time even as it stays fixed in space. In this picture, nothing is ever truly still, because everything is always advancing through the time dimension, always moving forward along its world line into the future. The genius of Minkowski's reformulation was to show that space-time has its own geometry, its own notion of distance that all observers can agree upon, even when they disagree about space and time separately. Recall that observers in relative motion disagree about lengths and about durations. One observer's meter is another's contracted length. One observer's second is another's dilated interval. These quantities are not absolute. They depend on the observer's motion. This might seem to leave physics in disarray, with no firm measurements anyone can agree on. But Minkowski found that there is a combined measure, blending space and time together in a particular way, that comes out the same for every observer, regardless of motion. This combined measure is called the space-time interval, and it plays the role in space-time that ordinary distance plays in space. Just as all observers agree on the true length of a rod, even when they view it from different angles, all observers agree on the space-time interval between two events, even when they disagree about how that interval divides up into space and time. The space-time interval is what is truly real and absolute in relativity. The separate space and time measurements are like shadows, projections of the true four-dimensional reality onto the particular perspective of each observer. When you and a fast-moving observer disagree about how much time passed between two events and how far apart in space they were, you are simply casting the same four-dimensional interval onto two different sets of axes, slicing it differently into space and time. The interval itself, the genuine separation between the events in the full fabric of space-time, is identical for both of you. This is why relativity, despite all its strangeness, does not collapse into pure subjectivity where nothing can be agreed upon. Beneath the shifting, observer-dependent measurements of space and time lies a solid, observer-independent structure, the geometry of space-time, on which everyone agrees. There is a subtle and important feature of how space and time combine in this interval, a feature that makes space-time geometry different from ordinary geometry. In the familiar geometry of space, distances are built by adding up the contributions from each direction. To find the straight line distance across a room, you combine the distances along each of the three spatial directions, and they all contribute in the same way, all added together. But time does not enter the space-time interval in the same way that space does. Time enters with an opposite sign. Rather than time and space simply adding together, the space-time interval involves the difference between the temporal part and the spatial part. This sign difference is not a mathematical curiosity. It is the source of much of what makes time different from space, the reason time has a distinct character and is not just another spatial direction. It is why we move freely through space, able to go forward and back, left and right, up and down, but seem compelled to move only forward through time. The geometry of space-time treats time and space as deeply related, yet not identical. They are unified, but the unification preserves an essential distinction between the time-like and the space-like. This distinction shows up in the way space-time sorts the relationships between events. Given any two events, the space-time interval between them can fall into one of a few categories, and these categories have profound physical meaning. If the interval is what physicists call time-like, then it is possible for something traveling slower than light to be present at both events, moving from one to the other. Such events lie within reach of each other. One can influence the other. There is a definite order to them that all observers agree upon, a genuine before and after, because a signal or an object could travel from the earlier to the later. If, on the other hand, the interval is space-like, then the two events are so far apart in space and so close in time that not even light could travel from one to the other. No influence can pass between them, and for such events, remarkably, different observers can disagree about their order. One observer may say the first happened before the second, another may say the reverse, and a third may say they were simultaneous. None of them is wrong, because no signal can connect the events, and so their ordering is not fixed by any chain of cause and effect. This is the deep structure underlying the relativity of simultaneity we encountered with the train and the lightning. Events that are space-like, separated, too far apart for light to bridge in the time available, have no absolute ordering. Their sequence is genuinely a matter of the observer's motion. But events that are time-like separated, close enough in space and far enough apart in time for light or slower signals to connect them, do have an absolute ordering, because always precedes effect for everyone. If one event causes another, every observer in the universe agrees that the cause came first. Relativity, for all its dissolution of absolute time, never permits effects to precede their causes. The dividing line between these two regimes, the boundary between what can influence what, is traced out by light itself, by the paths that light rays follow through space-time. These paths form what is called the light cone, the structure that separates the events you can affect or be affected by from those forever beyond your reach. Picture yourself at a single event, a single point in space-time here and now. From this point, imagine flashes of light spreading outward in all directions, racing away from you at the speed of light. As time passes, these flashes form an expanding sphere of light, growing larger and larger. Traced through space-time, this expanding sphere sweeps out a cone, opening up into the future. This is your future light cone, and it encloses every event you could possibly influence, every place a signal from you could reach, since nothing you send can travel faster than light. Anything outside this cone is beyond your power to affect, no matter what you do. There's also a mirror image cone opening into the past, containing every event that could have influenced you, every source from which a signal could have reached you by now. Together, these two cones, past and future, divide all of space-time into regions, the events you can affect, the events that can affect you, and the vast elsewhere that is causally cut off from your here and now. This light cone structure, present at every point in space-time, is the skeleton of causality in the universe, the framework that determines what can connect to what. It is a structure made possible only because the speed of light is constant and absolute, the same fixed barrier for everyone. And so even as Einstein dismantled the absolute time of Newton, he replaced it with a new absolute, the geometry of space-time and the light cones that thread through it, preserving order and causation in a universe where simultaneity itself had become relative. But all of this, remarkable as it is, described a universe without gravity, a smooth and empty space-time in which objects coast freely. The moment Einstein turned his attention to gravity, even this elegant structure would have to bend. The theory of special relativity, for all its power, contained a glaring gap, and Einstein knew it. It described a universe of observers moving at constant velocities, gliding smoothly through a flat and featureless space-time, but it said nothing about gravity. This was no small omission. Gravity is the most familiar force in all of nature, the force that holds us to the ground, that governs the falling of every object, that binds the moon to the earth and the earth to the sun, and the sun to the great wheeling mass of the galaxy. Any theory that claimed to describe space and time while ignoring gravity was incomplete. Worse than incomplete, special relativity actually clashed with the existing understanding of gravity in a way that could not be brushed aside. The conflict was fundamental, and resolving it would consume Einstein for the next decade and lead him to an even more radical reimagining of time and space. The trouble lay in Newton's law of gravity, the very law that had triumphed for 2 centuries. Newton described gravity as a force acting instantly across any distance. The sun pulls on the earth, and according to Newton, that pull is felt across the void of space without any delay whatsoever. If the sun were somehow to vanish in an instant, Newton's theory said the Earth would feel the loss of its gravitational grip immediately, at the very same moment, and would fly off into the darkness without pause. But special relativity had established something that flatly forbade this. Nothing, no object, no signal, no influence of any kind can travel faster than light. The speed of light is the ultimate speed limit of the universe, woven into the structure of space-time itself, an instantaneous force reaching across millions of kilometers in no time at all was simply impossible under the new understanding. If the sun vanished, the Earth could not possibly know until enough time had passed for the news to travel across the intervening distance at the speed of light, a journey of about 8 minutes. Newton's instantaneous gravity and Einstein's cosmic speed limit could not both be true. One of them had to give way. Einstein understood that gravity would need to be rebuilt from the ground up, made consistent with the principles of relativity. But he had no clear path forward, only a deep conviction that the answer existed and a willingness to think harder and longer than anyone else. The breakthrough, when it came, arrived not from equations but from one of his thought experiments, a simple imagined scenario that he would later call the happiest thought of his life. He pictured a person falling freely, perhaps from the roof of a building, perhaps in some other way detached from all support, and he realized something extraordinary about that person's experience. A person in free fall does not feel their own weight. They feel nothing pulling them down. For the duration of the fall, they are weightless, floating freely, as if gravity had been switched off entirely. This realization may seem modest, but Einstein saw in it the key to everything. Consider what it means. A person falling freely feels no gravity, even though gravity is precisely what is causing them to fall. If that same person were holding objects and released them, those objects would fall alongside them, hovering motionless before their eyes, drifting as though in empty space far from any planet. Inside a falling enclosure, cut off from any view of the outside, there would be no way to tell that you were falling in a gravitational field at all. Everything would behave exactly as it would in the depths of space, far from any source of gravity, where no gravitational force acted. The experience of free fall and the experience of floating in gravity-free space are, from the inside, completely identical. Gravity, in this sense, can be made to disappear simply by falling along with it. The flip side of this insight is equally striking. Imagine now a person inside a sealed room far out in empty space with no planet or star anywhere nearby, so that no gravity acts upon them. Ordinarily, they would float weightlessly. But suppose the room is attached to a rocket and the rocket fires its engines, accelerating the room steadily upward. The floor of the room rushes up to meet the floating person, pressing against their feet. Suddenly, they have weight again. They stand on the floor, feeling a force pushing up against them, exactly as if they were standing on the surface of a planet. If they dropped an object, it would fall to the floor because the floor accelerates up to meet it. Every experience inside this accelerating room in empty space would be indistinguishable from the experience of standing still in a gravitational field. The person inside, sealed off from any outside view, could not determine whether they were being held down by gravity or pushed along by the acceleration of a rocket. The two situations would feel exactly the same. This equivalence between gravity and acceleration is the cornerstone of everything that followed, and Einstein elevated it to a principle, the equivalence principle. It states that the effects of gravity and the effects of acceleration are locally indistinguishable, that no experiment confined to a small enough region can tell the difference between sitting in a gravitational field and being uniformly accelerated. Gravity and acceleration are, in a deep sense, the same thing seen from different points of view. This is a far stranger claim than it might first appear, and its consequences ripple outward in surprising directions. For if gravity is equivalent to acceleration, and if we already know from special relativity that motion affects the passage of time, then gravity itself must affect the passage of time. The link is direct and unavoidable. Acceleration and gravity are equivalent, motion influences time, and so gravity must influence time as well. This was the thread that would lead Einstein to the conclusion that gravity slows the flow of time, that clocks run at different rates depending on where they sit within a gravitational field. To see how the equivalence principle forces this conclusion, consider light traveling inside the accelerating rocket room. Imagine a beam of light crossing the room horizontally, sent from one wall toward the opposite wall. In the brief time the light takes to cross, the room, accelerating upward, has moved. The far wall has shifted up slightly during the light's journey. So when the light reaches the opposite wall, it strikes a point slightly lower than where it started, because the wall rose to meet it while the light was in transit. From the perspective of someone inside the room, the beam of light appears to bend downward, curving toward the floor as it crosses. This is a direct consequence of the room's acceleration. But now apply the equivalence principle. If acceleration causes light to bend, and acceleration is indistinguishable from gravity, then gravity must cause light to bend as well. Light passing through a gravitational field should curve, bending toward the source of gravity, just as it bent toward the floor of the accelerating room. This was one of the first concrete and testable predictions to emerge from Einstein's new thinking, the bending of light by gravity, and it would later provide one of the most dramatic confirmations of his entire theory. The bending of light hints at something deeper still. Light, left to itself, travels in straight lines. It is the very definition of straightness, the path that a ray of light takes through empty space. So if light bends as it passes through a gravitational field, and light always travels in straight lines, then the only way to reconcile these facts is to conclude that space itself is bent. The light is still traveling as straight as it possibly can, but the space through which it travels is curved, and so the straightest possible path is itself a curve. This is the revolutionary idea at the heart of Einstein's theory of gravity. Gravity is not a force in the ordinary sense, not a pull transmitted across space like a rope tugging an object. Gravity is the curvature of space-time itself. Massive objects bend the fabric of space-time around them, and other objects moving through this curved space-time follow the straightest paths available to them, paths that appear curved to us precisely because the underlying space-time is curved. The planets do not orbit the sun because the sun reaches out and pulls them. They orbit because the sun has curved the space-time around it, and the planets are simply coasting along the straightest paths through that curved geometry, like marbles rolling along the contours of a warped surface. This was the central insight of what came to be called general relativity, the theory Einstein completed in the year 1915, a full decade after special relativity. The name reflects that it generalized the earlier theory to include gravity and accelerated motion, where special relativity had handled only the special case of constant velocity, and it transformed our understanding of gravity completely. Where Newton saw a mysterious force reaching invisibly across space, Einstein saw geometry, the bending and warping of space-time by the matter and energy within it. A massive body tells space-time how to curve, and curved space-time tells matter how to move. The two are locked together in an intricate dance, mass shaping geometry and geometry guiding mass. Gravity, the oldest and most familiar of forces, was revealed to be not a force at all, but the shape of the universe responding to what fills it. And because time is part of space-time, woven into the same fabric as space, the curvature of space-time affects not only the paths objects take through space, but the rate at which time itself flows. To understand how gravity reshapes time, we need to look closely at what happens to a clock when it sits deep within the curve of a gravitational field, and the answer reveals that even the ground beneath your feet is quietly distorting the passage of time. The conclusion that gravity slows time follows directly from the equivalence principle, and it can be traced through a simple line of reasoning. Return once more to the accelerating rocket room, but now place a clock at the ceiling and an identical clock at the floor. The clock at the ceiling sends a signal downward to the clock at the floor, a pulse of light marking the passage of each second. As each pulse travels down toward the floor, accelerating upward, rushes to meet it. Because the floor is racing toward the descending signals, it encounters them more frequently than it otherwise would, receiving the pulses at a faster rate than the ceiling clock sent them. To an observer at the floor, the ceiling clock appears to be ticking quickly, running fast, sending its seconds in a hurry. Conversely, signals sent from the floor up to the ceiling arrive less frequently, because the ceiling is accelerating away from them, and so the floor clock appears to the ceiling observer to run slow. Now, invoke the equivalence principle once again. The accelerating rocket room is indistinguishable from a room sitting in a gravitational field, with the floor corresponding to the position lower in the field, nearer the source of gravity, and the ceiling corresponding to the position higher up. The conclusion carries over directly. A clock higher in a gravitational field runs faster than a clock lower down. A clock closer to a massive body, deeper in the gravitational well, ticks more slowly than a clock farther away. Time itself runs at different rates at different heights within a gravitational field, slower where gravity is stronger, faster where gravity is weaker. This effect is called gravitational time dilation, and it is distinct from the time dilation caused by motion, though both spring from the same underlying unity of space and time. Where the motion-based effect depended on how fast a clock moved, this gravitational effect depends on where the clock sits within the curvature of space-time. The practical meaning of this is genuinely surprising. It means that time passes more slowly at sea level than on a mountaintop. It means that time passes more slowly on the ground floor of a building than on the top floor. It means, taken to its logical conclusion, that your feet age more slowly than your head, because your feet are slightly deeper in the Earth's gravitational field than your head is. The difference is staggeringly small under ordinary circumstances, far too tiny to notice or to matter for any practical purpose in daily life. Over an entire human lifetime, the difference in aging between your head and your feet amounts to a fraction of a second, immeasurable by any ordinary means. But the difference is real. It is not a figure of speech or a loose way of talking. Time genuinely flows at different rates at different elevations. And the only reason we never noticed throughout all of history is that the effect is so minuscule at the gravitational strengths we ordinarily encounter. What makes this more than a theoretical claim is that the effect has been measured directly, with clocks precise enough to detect even these vanishingly small differences. In recent years, atomic clocks have become so extraordinarily accurate that they can detect the difference in the flow of time caused by raising a clock by mere centimeters. Lift one such clock a small distance above another, and it will tick measurably faster by exactly the amount Einstein's theory predicts. The clock at the higher elevation, slightly farther from the center of the Earth and thus slightly higher in the gravitational field, runs faster than its twin below. These experiments have confirmed gravitational time dilation down to the smallest scales, demonstrating that the warping of time by gravity is real even within the space of a single room, even across a difference in height you could measure with your hand. The flow of time is not uniform, even within the volume of an ordinary building. Every step you climb lifts you into a region where time passes very slightly faster. The same effect was confirmed on a larger scale decades earlier in an experiment of remarkable delicacy. Physicists measured the difference in the flow of time between the top and bottom of a tower using the precise frequencies of radiation emitted by atoms as their clocks. Radiation, climbing up out of the Earth's gravitational field from the bottom of the tower to the top, was found to shift in frequency by exactly the amount gravitational time dilation predicted, its oscillations stretching out as it climbed away from the stronger gravity below. This shifting of frequency as light moves through a gravitational field is called gravitational redshift, and it is the direct observational signature of gravity's effect on time. Light climbing out of a gravitational well loses energy, not by slowing down, for light never changes speed, but by stretching to longer wavelengths, shifting toward the red end of the spectrum. The deeper the well the light climbs out of, the greater the shift. Astronomers observe this redshift in the light from dense, massive stars, whose powerful gravity stretches the light leaving their surfaces, and the measured shifts match the predictions of general relativity. There's a beautiful way to understand why light shifts in this manner, tying gravitational redshift directly back to time dilation. Think of a wave of light as a kind of clock, ticking off each oscillation as a crest passes. The frequency of the light, the number of oscillations per second, is set by the clock at the place where the light was emitted. If that clock runs slow because it sits deep in a gravitational field, then the light it emits will have a lower frequency, fewer oscillations per second as judged by an observer higher up where time runs faster. The light from below arrives stretched out, redshifted, precisely because it was emitted by a clock running slow in the stronger gravity below. The redshift of the light is nothing other than the time dilation of its source, made visible. The slowing of time deep in a gravitational well and the reddening of light climbing out of that well are two ways of describing the very same phenomenon. Gravity slows the clocks, and the slowed clocks emit reddened light. This deep connection between gravity, time, and the behavior of light underscores how thoroughly Einstein had transformed the concept of time. Time was no longer a fixed universal background. It had become a local quantity, varying from place to place depending on the strength of gravity, flowing at different rates in the valley and on the peak, near the massive star and far from it. Each location in the universe has its own rate of time, set by the curvature of space-time at that point, by how deeply that location sits within the gravitational wells created by all the surrounding matter. There is no single cosmic time governing all of existence. There is only the local time at each place, ticking at its own rate, slower where gravity grips strongly and faster where it relaxes. The universe is filled with a vast multitude of clocks, each running at the rate dictated by its position in the curved geometry of space-time, and no two clocks at different depths in the gravitational landscape keep quite the same time. It would be tempting to dismiss all of this as the concern of physicists and philosophers, fascinating in principle but irrelevant to ordinary existence. For most of human history, that would have been a fair assessment. The effects are so small at the gravitational strengths we encounter on Earth and at the speeds we ordinarily travel that they have no bearing on daily life as it was lived for thousands of years. No farmer planting crops, no merchant counting coins, no traveler crossing a continent ever needed to account for the relativity of time. The universal time of Newton served perfectly well for every practical purpose anyone had ever encountered. But this changed in the modern era and changed dramatically with the development of a technology that now sits in nearly every pocket and guides nearly every journey. The satellite navigation systems that tell us where we are on the surface of the Earth depend on a network of clocks orbiting high above us, and those clocks experience both kinds of time dilation at once, the slowing from their motion and the speeding from their altitude. If the engineers who built these systems had ignored Einstein, if they had assumed that time flows at the same rate in orbit as on the ground, the entire system would fail, and fail quickly. The story of how relativity became a matter of everyday engineering, woven invisibly into the technology of modern life, is perhaps the most convincing proof of all that Einstein was right. The satellite navigation system that guides cars, ships, aircraft, and pedestrians across the surface of the Earth works on a principle of beautiful simplicity, and it depends entirely on the precise measurement of time. High above the planet, a constellation of satellites circles in orbit, each one carrying an extremely accurate atomic clock and continuously broadcasting signals that announce the satellite's position and the exact time the signal was sent. A receiver on the ground, in a phone or a vehicle or a handheld device, listens for these signals from several satellites at once. By noting the tiny differences in when each signal arrives, the receiver can calculate how far away each satellite is, since the signals travel at the known speed of light, and a later arrival means a greater distance. With distances to several satellites in hand, the receiver can pinpoint its own location on the Earth's surface, often to within a few meters. The entire system is, at its heart, a method of triangulating position from the timing of light signals, and its accuracy depends utterly on the clocks aboard the satellites keeping nearly perfect time. Here is where relativity enters, and it enters with consequences too large to ignore. The satellites are not sitting still on the ground. They are moving rapidly, racing around their orbits at thousands of kilometers per hour, and they are positioned high above the Earth, far up in a region where the planet's gravitational field is weaker than it is at the surface. Both of these facts affect the rate at which the satellite clocks tick, and they do so in opposite directions. The motion of the satellites, by the time dilation of special relativity, causes their clocks to run slow relative to clocks on the ground. The faster a clock moves, the more it falls behind, and the satellites are moving fast enough for this effect to register. At the same time, the satellite's high altitude, by the gravitational time dilation of general relativity, causes their clocks to run fast relative to clocks on the ground. Higher in the gravitational field where gravity is weaker, time flows more quickly, and the satellites are high enough for this effect to register as well. The two effects pull in opposite directions, one slowing the satellite clocks and the other speeding them up. The two effects do not cancel out, They are of different sizes, and the gravitational effect, the speeding up due to altitude, is the larger of the two. When the calculations are done, the motion of the satellites slows their clocks by a certain amount each day, while their altitude speeds their clocks by a larger amount each day. And the net result is that the satellite clocks run fast compared to clocks on the ground, gaining a small but definite amount of time every single day. The amount is around several tens of millionths of a second per day. This sounds utterly negligible, the kind of difference no human being could ever perceive, the kind of error that surely could not matter for any practical purpose. But in the context of satellite navigation, it matters enormously, because the system depends on timing signals that travel at the speed of light, and at the speed of light, even a tiny error in time translates into a large error in distance. Consider what a timing error of millionths of a second means when the signals travel at the speed of light. Light covers about 300,000 kilometers every second, which means it covers about 300 meters in a millionth of a second. So an error of even a few tens of millionths of a second in the satellite clocks would translate, through the navigation calculation, into a position error of many kilometers, and that error would grow with each passing day as the clocks drifted further out of agreement with the ground. If the relativistic effects were simply ignored, if the satellite clocks were allowed to run according to their own fast rate, without correction, the navigation system would produce positions that were wrong by several kilometers within a single day, and the errors would accumulate without bound thereafter. A navigation system that placed you several kilometers from your true location and grew worse by the hour would be worse than useless. It would be a system that did not work at all. The entire technology would collapse within hours of being switched on if Einstein's corrections were left out. The engineers who designed these systems understood this perfectly, and they built the corrections for relativity directly into the system from the start. The atomic clocks aboard the satellites are deliberately adjusted before launch so that they tick at a rate slightly different from an identical clock on the ground, set to a rate that, once the satellite is in orbit and experiencing the combined effects of its motion and altitude, will bring it into agreement with ground time. The clocks are, in effect, pre-corrected for relativity, tuned to run at the wrong rate on the ground so that they will run at the right rate once they are in orbit and time is flowing differently for them. Beyond this built-in adjustment, the system continuously monitors and fine-tunes the clocks to keep them synchronized with ground time to extraordinary precision. Every time someone uses satellite navigation to find their way, the device in their hand is silently relying on calculations that account for the warping of time by motion and gravity, calculations that would have been meaningless before Einstein. The relativity of time, once an abstract conclusion drawn from thought experiments about trains and light beams, has become an engineering necessity, checked and confirmed billions of times every day by the simple fact that the navigation works. There is something profound in this. The satellite navigation system is, in a sense, a continuous and global experiment confirming the predictions of relativity, an experiment running constantly, every moment of every day, all across the world. Each successful navigation, each accurate position fix, each correctly routed journey is a small confirmation that time really does run at different rates depending on motion and gravity, exactly as Einstein worked out a century ago, with nothing but reasoning and imagination. If his theory were wrong, the system would fail visibly and immediately, and there would be no hiding it. Instead, the system works flawlessly, day after day, year after year, a quiet and overwhelming testament to the accuracy of the strangest ideas in physics. The relativity of time is not a speculation awaiting confirmation. It is a verified feature of reality, demonstrated by the technology that guides the everyday movements of much of humanity. This brings home a point worth dwelling on. The effects of relativity are often described as relevant only in extreme circumstances, near the speed of light or in the crushing gravity of exotic objects, far removed from anything we will ever encounter. And it is true that the effects become dramatic only in such extremes, but they are not absent in ordinary life. They are present always, everywhere, woven into the fabric of every moment, simply too small to notice without instruments of great precision. Every time you climb a flight of stairs, time speeds up for you by an amount too tiny to feel but entirely real. Every time you travel in a vehicle, time slows for you by a similarly imperceptible amount. The satellites overhead experience these effects strongly enough that we are forced to account for them. But the same effects touch every object that moves and every object that sits within a gravitational field, which is to say, every object in the universe. Relativity is not a remote and exotic theory describing distant phenomena. It describes the world we live in, the ordinary world of stairs and journeys and clocks, accurately revealing that even here, in the most mundane circumstances, time is not the fixed and universal thing it appears to be. Having seen how relativity governs time in the gentle gravity of the Earth and the modest speeds of satellites, we are prepared to follow its predictions into far more extreme territory, where gravity grows not slightly, but overwhelmingly strong, where the warping of time becomes not a matter of millionths of a second, but a transformation so profound that time itself seems to come undone. The same equations that correct our navigation systems by tiny fractions also predict the existence of regions where gravity becomes so intense that it tears the ordinary relationship between space and time apart entirely. These regions are the black holes, the most extreme manifestations of curved spacetime that the universe contains, and at their edges, the behavior of time becomes stranger than anywhere else in the cosmos. To understand what relativity says about time in its most extreme form, we must approach one of these objects and watch what happens to a clock as it falls toward the point of no return. A black hole is what remains when gravity wins completely, when matter is compressed so densely that the curvature of spacetime around it becomes overwhelming. To understand how such an object forms, consider the life of a massive star. Throughout its existence, a star maintains a delicate balance. The immense gravity of its own mass pulls relentlessly inward, trying to collapse the star upon itself, while the energy generated by nuclear reactions in its core pushes outward, holding the star up against its own weight. For millions or billions of years, these two forces remain in balance, and the star shines steadily. But the nuclear fuel cannot last forever. Eventually, it runs out, the outward push fades, and gravity, which never tires and never relents, finally overwhelms everything. The core of the star collapses inward. For the most massive stars, nothing in nature can halt this collapse. The matter is crushed inward without limit, packed into an ever smaller volume, the gravity growing more intense as the matter concentrates, until the curvature of spacetime becomes so extreme that a region forms from which nothing can escape, not even light. This region is a black hole. The defining feature of a black hole is its boundary, a surface called the event horizon. This is not a physical surface, not a wall or a membrane of any material substance. It is a boundary in spacetime, a threshold marking the point of no return. Outside the event horizon, it is still possible, with enough speed, to escape the black hole's gravity and travel away. At the event horizon, the gravity becomes so strong that the speed required to escape reaches the speed of light itself. And inside the event horizon, escape would require exceeding the speed of light, which nothing can do. So anything that crosses the event horizon, any object, any particle, any ray of light, is trapped forever, doomed to fall inward toward the center with no possibility of return. The event horizon is a one-way boundary in spacetime. Things can fall in, but nothing can come back out. It is the surface beyond which the black hole's interior is sealed off from the rest of the universe, hidden behind a horizon that no signal can ever cross from the inside. What happens to time near this boundary is among the most extreme predictions of general relativity, and it follows directly from the gravitational time dilation we have already encountered, taken to its ultimate limit. We saw that time runs more slowly deeper in a gravitational field, slower in the valley than on the peak, slower near a massive star than far from it. As gravity grows stronger, the slowing of time grows more pronounced. Near a black hole, where gravity becomes more intense than anywhere else in the universe, the slowing of time becomes extreme beyond anything encountered elsewhere. And at the event horizon itself, where the gravity reaches the ultimate threshold, the slowing of time, as seen by a distant observer, becomes total. Time, from the perspective of someone watching from far away, comes to a complete stop at the event horizon. This is not an exaggeration or a loose manner of speaking. It is the literal prediction of the theory. A clock approaching the event horizon of a black hole runs slower and slower, as judged by a distant observer, until at the horizon it appears to stop entirely. Frozen at the threshold, its final tick stretched out across all of eternity. To make this concrete, imagine an observer falling toward a black hole while a companion watches from a safe distance far away. Suppose the falling observer carries a bright light and a clock, and the distant companion watches both as the fall proceeds. From the perspective of the distant companion, something remarkable unfolds as the falling observer approaches the event horizon. The falling observer's clock, watched from afar, ticks more and more slowly. The observer's motion seems to slow, their fall dragging out, taking longer and longer to cover each remaining bit of distance to the horizon. The light they carry shifts toward the red, its frequency lowering as it climbs out of the deepening gravitational well, growing dimmer and redder as the fall continues. And as the falling observer draws ever nearer to the event horizon, this slowing intensifies without bound. The observer appears to approach the horizon but never quite reach it, their motion freezing, their clock halting, their image fading to red and then dimming toward darkness. To the distant companion, the falling observer never actually crosses the event horizon at all. They are frozen forever at its edge, their final approach stretched across infinite time, an image lingering at the threshold and slowly fading from view. This is why black holes were once described by a different name, frozen stars, because matter falling into them appears from the outside to freeze at the horizon rather than disappear within. The collapsing star itself, as it forms a black hole, appears from the outside to slow in its collapse and freeze at the forming horizon, never quite completing its plunge as judged by distant observers. The surface of the dying star seems to hover at the event horizon for all eternity, its light reddening and dimming until it fades beyond detection. From the outside, nothing ever truly falls in. Everything piles up at the horizon, frozen in time, its light stretched and faded into invisibility. The black hole appears from a distance to be surrounded by a shell of frozen, fading images of everything that ever fell toward it, each one halted at the threshold, each one a moment stretched across infinity. But here, the theory reveals one of its most profound and subtle features, for the experience of the falling observer is entirely different from what the distant companion sees. This is the same lesson we learned from the relativity of simultaneity, raised to its most dramatic form. The two perspectives do not agree, and neither is wrong. For the distant companion, the falling observer freezes forever at the horizon. But for the falling observer, nothing of the sort happens. From the falling observer's own point of view, time proceeds perfectly normally. Their clock ticks at its usual rate. They feel no slowing, no freezing, no stretching of time. They fall toward the black hole, reach the event horizon, and cross it, all in a finite and ordinary span of time as measured by their own clock. There is no barrier at the event horizon as they experience it, no wall, no moment of freezing. They pass through it smoothly, perhaps without even noticing the precise moment of crossing, and continue falling inward toward the center. For the falling observer, the journey across the event horizon is uneventful in its timing, a continuous fall that carries them across the threshold and into the interior in finite time. How can these two perspectives both be true? How can the falling observer cross the horizon in finite time while the distant companion sees them frozen at the horizon forever? The answer lies in the radical way that black holes distort the relationship between space and time, and in the fact that the two observers are separated by the event horizon, which prevents them from ever reconciling their views by direct comparison. Once the falling observer crosses the horizon, no signal they send can ever reach the distant companion, because no signal can escape from within the horizon. So the distant companion can never see the crossing, and from their vantage point, the crossing never happens, the falling observer remaining eternally frozen at the threshold. The falling observer, meanwhile, sails through and can never report back. The two perspectives are forever separated by the horizon, each self consistent within its own domain, neither able to contradict the other because no information can pass between them. The disagreement about whether and when the horizon is crossed is not a paradox to be resolved by deciding who is right. It is a genuine feature of how space-time is structured around a black hole, a place where the flow of time becomes so distorted that two observers can permanently disagree about whether an event has even occurred. This raises a question that pushes against the very limits of what the theory can describe. If time stops at the event horizon for an outside observer, and if the relationship between space and time becomes so distorted there, what happens to time inside the event horizon, beyond the point of no return? What becomes of time in the deep interior of a black hole, where the curvature of space-time grows toward infinity at the central point of collapse? Here, the theory makes a prediction stranger than anything we have yet encountered, a prediction about the fate of time itself inside the horizon, where space and time exchange their roles and the structure of reality as we know it begins to break down. To follow this thread, we must cross the event horizon ourselves, at least in imagination, and ask what the theory says about the nature of time in the one place in the universe from which no answer can ever return. Crossing the event horizon in imagination, following the falling observer past the point of no return, we enter a region where the predictions of general relativity become stranger than anywhere else, and where time undergoes a transformation that defies ordinary understanding. Outside a black hole, in the space-time we are familiar with, you can move freely through space in any direction, but you are carried inevitably forward through time. You can choose to go left or right, up or down, forward or back in space, but you cannot choose to stop moving through time or to reverse your motion through it. Time carries you forward whether you will it or not. This is the ordinary structure of space-time, with space offering freedom of movement and time imposing an inexorable forward march. Inside the event horizon of a black hole, this structure undergoes a remarkable inversion. Within the event horizon, the roles of space and time, in a precise mathematical sense, become exchanged. The direction that points toward the center of the black hole, the direction of decreasing distance from the central singularity, takes on the character that time has in ordinary space. It becomes a direction you are compelled to move along, just as you are compelled to move forward in time outside the hole. Inside the horizon, falling toward the center is no longer a choice, but an inevitability, as unavoidable as the passage of time itself. You cannot stop your fall toward the center any more than you can stop yourself from aging in ordinary life. The center of the black hole becomes not a place in space that you might steer toward or away from, but a moment in your future that you cannot avoid, as certain to arrive as tomorrow. No matter what you do, no matter how you fire your engines or struggle against your fate, you will reach the center, because the center has become part of your future rather than a location in your space. The pull toward the singularity is not a force you might resist. It is the flow of time itself, redirected toward the center. This exchange of space and time inside the horizon is one of the most conceptually difficult features of black holes, and it reveals how thoroughly general relativity overturns our ordinary intuitions about the nature of time. Time is not a fixed and absolute thing flowing uniformly throughout the universe. It is woven into the geometry of space-time, and where that geometry becomes extreme, as it does inside a black hole, time can take on roles and behaviors utterly foreign to our experience. The very distinction between space and time, which seems so fundamental and clear in ordinary life, turns out to be a feature of the particular gentle geometry we happen to inhabit, not an absolute and universal law. In the extreme geometry inside a black hole, that distinction blurs and inverts, and what was a direction in space becomes a direction in time. The fixed, reliable forward flow of time that governs all of our experience is revealed to be local and contingent, a property of our region of space-time rather than an unbreakable rule of reality. At the very center of the black hole lies the singularity, the point toward which all infalling matter is driven, and here, general relativity reaches the limit of its own validity. At the singularity, the curvature of spacetime, according to the theory, grows without bound, becoming infinite. The matter that formed the black hole, and everything that has fallen in since, is crushed toward this central point of infinite curvature, compressed beyond any density, beyond any limit the ordinary laws of physics can describe. And time itself, for the infalling observer, comes to an end at the singularity. This is not a freezing of time as seen from outside, but something more final. The singularity represents the end of the world line of anything that reaches it, the termination of its path through spacetime, a future boundary beyond which the theory simply offers no continuation. For the falling observer, the singularity is not a place they arrive at and then leave. It is the end of their time, the final moment of their existence, beyond which there is no later moment for the theory to describe. The appearance of infinities in the description of the singularity is a signal that general relativity, for all its triumphs, has reached the boundary of its applicability. Throughout the history of physics, when a theory predicts an infinite quantity, it is usually a sign that the theory has been pushed beyond the range where it can be trusted, that some deeper theory is needed to describe what truly happens. The infinite curvature at the singularity is widely understood as such a signal. General relativity describes spacetime as a smooth and continuous fabric, and this description works magnificently across an enormous range of circumstances, from the gentle gravity of the Earth to the extreme warping near the event horizon of a black hole. But at the singularity, where curvature becomes infinite and densities become unlimited, the smooth description must break down. Something else must take over, some deeper theory that can describe what happens to space, time, and matter under conditions so extreme that the very notions of space and time may lose their ordinary meaning. What that deeper theory is, physicists do not yet know with certainty, but the singularity stands as a marker of where our current understanding ends. It is worth pausing to consider what the singularity means for the nature of time itself. Outside the black hole, time stretches without end into the future, every moment followed by another, the world line of every object continuing indefinitely onward. But at the singularity inside a black hole, time, for the infalling observer, simply ceases. There's a last moment, beyond which the theory provides nothing. No further moments, no continuation, no later. This is a profound and unsettling notion. We are accustomed to thinking of time as boundless, as something that always continues, that has no edge or end. The singularity suggests that time can have a boundary, a final moment beyond which there is no after, at least within the framework of general relativity. Whether this truly represents the end of time for the infalling matter, or whether a deeper theory would reveal some continuation that general relativity cannot capture, remains one of the great open questions of physics. The singularity marks not just the center of a black hole, but the edge of our knowledge, the place where time, as we understand it, comes to an end and the theory falls silent. The strange behavior of time inside a black hole, however, points toward a larger and even more fundamental question about the nature of time throughout the universe. We have seen that time is local, varying from place to place with motion and gravity. We have seen that simultaneity is relative, that observers disagree about the ordering of events. We have seen that time can stop, exchange roles with space, and even come to an end at a singularity. All of these discoveries undermine the comfortable, intuitive picture of time as a universal river flowing uniformly forward, carrying all of existence along together. But if that picture is wrong, what should replace it? If there is no universal now, no shared present moment ticking forward for the whole cosmos, then how should we understand the relationship between past, present, and future? Relativity hints at an answer to this question, an answer that is in some ways more radical than anything we have yet considered. A vision of time in which the distinction between past, present, and future loses its absolute meaning, and all of existence is understood as a single unchanging whole. To explore this vision, We need to widen our view from individual black holes to the structure of time across the entire universe and ask what relativity implies about the deepest nature of past, present, and future. Before considering what relativity implies about the deepest nature of past, present, and future, it is worth stepping back to take in the universe as a whole, for the same theory that bends time around stars and black holes also describes the structure and history of the entire cosmos. When Einstein completed general relativity, he had built a theory of space-time that applied not just to individual objects and their gravity, but to the universe in its entirety. Space-time, with all its matter and energy, could be treated as a single system governed by the equations of the theory, and physicists soon began to ask what those equations implied about the universe at the largest scales. The answer that emerged was as surprising as anything in relativity, and it carried profound implications for the nature of time, suggesting that time and the universe itself had a beginning, a definite starting point from which everything we see has unfolded. When the equations of general relativity were first applied to the universe as a whole, they delivered an unexpected verdict. They indicated that the universe could not be static, could not be sitting still and unchanging as had always been assumed. The equations insisted that the universe must be either expanding or contracting, growing larger or shrinking smaller, but never standing still. This conclusion was so contrary to expectation that Einstein himself initially resisted it. The prevailing belief at the time was that the universe was eternal and unchanging on the largest scales, a fixed and permanent stage. So convinced was Einstein of this that he modified his own equations, introducing an additional term specifically designed to hold the universe still, to balance the tendency toward expansion or contraction, and produce the static universe everyone expected. This term, which he later regarded as a mistake, was an artificial addition meant to preserve a belief that observation would soon overturn. For observation did overturn it. Astronomers studying distant galaxies discovered that those galaxies were, almost without exception, moving away from us and moving away faster the more distant they were. The light from these galaxies was shifted toward the red end of the spectrum, stretched to longer wavelengths in a manner that indicated they were receding. The farther away a galaxy lay, the greater this redshift, the faster it was moving away. This pattern, the same in every direction astronomers looked, pointed to an unmistakable conclusion. The universe was expanding. Space itself was stretching, carrying the galaxies apart from one another, the whole cosmos growing larger with the passage of time. This was exactly what general relativity had predicted before Einstein added his corrective term to suppress it. The universe was not static after all. It was dynamic, evolving, expanding outward, and Einstein abandoned his added term, reportedly regarding its introduction as the greatest blunder of his career. The discovery that the universe is expanding carries a remarkable implication when you run the process backward in time. If the universe is growing larger as time moves forward, with the galaxies spreading apart, then, in the past, the universe must have been smaller, the galaxies closer together. And if you continue running the clock backward, the universe becomes smaller and smaller, denser and denser, the matter packed ever more tightly together. Carried to its conclusion, this reasoning leads to a moment in the distant past when the entire universe was compressed into an extraordinarily small, dense, hot state from which it has been expanding ever since. This moment, the beginning of the expansion, is what we call the Big Bang, the origin of the universe as we know it, dated to roughly 14 billion years ago. The Big Bang was not an explosion within space, scattering matter into a pre-existing void. It was the beginning of the expansion of space itself, the origin point from which space and time and matter all emerged and began their evolution. This conclusion transformed our understanding of time at the largest scale. Time, it appeared, was not infinite into the past. It had a beginning. There was a first moment, an origin, before which, in a meaningful sense, there was no before. The Big Bang represents not just the beginning of matter and energy, but the beginning of time itself, the origin of the temporal dimension along with the spatial ones. This is a difficult notion to grasp, for we naturally want to ask what came before the Big Bang, what existed prior to that first moment. But if the Big Bang was the beginning of time, then the question of what came before may have no meaning, for there was no before, no earlier moment, no time at all prior to the origin of time. Asking what came before the beginning of time is like asking what lies north of the North Pole. The question assumes a direction that does not exist, a moment earlier than the first moment, which is a contradiction in terms. Time itself began at the Big Bang, and the notion of before loses its meaning at that boundary. This idea connects in a striking way to what we encountered at the singularity inside a black hole. Just as the singularity at the center of a black hole represents an end of time for the infalling observer, a boundary beyond which the world line does not continue, the Big Bang represents a beginning of time for the universe, a boundary before which there were no earlier moments. In both cases, we encounter an edge to time, a place where the smooth, continuous flow that we ordinarily experience reaches a limit. And in both cases, the curvature of space-time becomes extreme, growing toward infinity, signaling that general relativity has reached the boundary of its validity, that some deeper theory is needed to describe what truly happens at these edges. The Big Bang, like the singularity in a black hole, is a place where our current understanding falls silent, where the equations break down and the true nature of time becomes uncertain. Whether time truly began at the Big Bang, or whether some deeper theory would reveal a continuation, a before that general relativity cannot capture, remains among the deepest open questions in all of physics. The expansion of the universe also reveals something profound about the relationship between time and the large-scale structure of the cosmos. Because light travels at a finite speed, looking out into space is also looking back in time. When you observe a distant galaxy, you see it not as it is now, but as it was when the light left it, millions or billions of years ago. The farther away an object lies, the further back in time we see it, the older the light by which we observe it. This means that the universe presents us with a kind of visible history, a record of the past laid out across the depths of space, the most distant objects showing us the universe as it was in its youth. Astronomers, peering at the faintest and most distant light, can observe the universe as it appeared not long after the Big Bang, can study the conditions of its early history directly by collecting light that has been traveling toward us across nearly the entire age of the cosmos. The night sky is not a snapshot of the present, but a layered tapestry of different epochs, each star and galaxy showing us a different moment in the past, the whole arranged by distance into a vast chronicle of cosmic time. There's even a faint glow that fills the entire sky in all directions, a relic of the early universe, the light released when the cosmos had cooled enough for the first atoms to form, a few 100,000 years after the Big Bang. This ancient light, stretched by the expansion of the universe across billions of years into a faint microwave glow, is the oldest light we can observe, a direct image of the universe as it was in its infancy. It is the most distant thing we can see, and the furthest back in time, a snapshot of the cosmos from near the very beginning. The existence of this glow, predicted by the theory of an expanding universe that began in a hot, dense state and then discovered exactly as predicted, stands as powerful confirmation that the universe really did emerge from a Big Bang, really did have a beginning, really does have a history written in light across the sky. Time at the cosmic scale is not an eternal and featureless backdrop, but a dimension with a definite origin and a rich, evolving history, recorded in the light that reaches us from the depths of space. And this cosmic history, with its definite beginning and its forward unfolding, brings us back to the deepest question. Relativity raises about time, the question of whether the flow we experience, the passage from past through present to future, reflects something real about the universe, or whether it is, in some profound sense, an illusion. The question of whether the passage of time is real, or whether it is, in some sense, an illusion, arises naturally from everything relativity has revealed, and it leads to one of the most provocative ideas in modern physics. We have seen that there is no universal now, no shared present moment ticking forward for the entire cosmos. Observers in relative motion disagree about which events are simultaneous, slicing the universe into present moments in different ways, none more correct than another. This dissolution of the universal present has a startling implication when followed to its conclusion. If there is no objective, universal present moment, then perhaps the distinction between past, present, and future is not a fundamental feature of reality at all. Perhaps it is something that depends on the observer, like simultaneity itself, rather than a deep truth about the universe. And if that is so, then perhaps past, present, and future all exist in the same way, all equally real, with the sense of time flowing from one to the next being a feature of our experience rather than a feature of the universe. This is the idea sometimes called the block universe, and it follows from taking the space-time picture of relativity at face value. Recall that relativity describes reality as a four-dimensional space-time in which every event has a fixed location marked by its three spatial coordinates and its one temporal coordinate. In this picture, the entire history of the universe, every event that has ever happened or ever will happen, exists as a fixed structure in four-dimensional space-time, laid out completely from beginning to end. Your birth, this moment, your death, the formation of the sun, its eventual demise, all of these are simply locations within the four-dimensional block, all equally present in the structure of space-time, all equally real. In this view, the universe does not unfold moment by moment, with the future coming into existence as the present slips into the past. Instead, the whole of space-time, past and future together, simply exists, a single, unchanging four-dimensional whole, complete and entire. The future is not open and undetermined, waiting to be created. It already exists out there in the block, as fixed and real as the past. This way of thinking about time strikes most people as deeply counterintuitive, even disturbing, for it seems to deny something we feel with absolute certainty: the flow of time, the vivid sense that the present moment is special, that the past is gone and the future is yet to come, that time is passing. We experience time as a flow, a continuous movement from one moment to the next, the future steadily becoming the present and the present steadily receding into the past. This sense of flow is among the most basic features of conscious experience, as fundamental to how we live as anything could be. The block universe seems to say that this flow is, in some sense, not real, that it does not correspond to anything in the actual structure of space-time, that it is a feature of how we experience the universe rather than a feature of the universe itself. All moments exist equally in the block, and the sense that one particular moment is the privileged present, with the past fixed behind it and the future open ahead, is, in this view, a kind of perspective, the way the unchanging block appears from within the experience of a conscious being moving along their world line. The argument for the block universe draws considerable force from the relativity of simultaneity, and the connection is worth drawing out carefully. Consider two observers in relative motion passing each other at some moment. Because they are moving relative to each other, they slice space-time into present moments differently. For one observer, a particular distant event lies in the present. For the other, that same event might lie in the past or the future. Each observer has an equally valid claim to their own present, their own slicing of the universe into past, present, and future. But here is the crucial point. If one observer's present includes events that another observer places in the future, and both observers are equally correct, then those future events must be just as real as present ones, for they lie in someone's legitimately defined present. The future of one observer is the present of another. And since neither observer is privileged, neither slicing more correct than the other, the events must simply exist, real, regardless of whose present they fall into. This reasoning suggests that all events, past, present, and future, share the same reality, exactly as the block universe proposes. The relativity of simultaneity, by denying any universal present, seems to imply that the future is as fixed and real as the past, that all of space-time exists together as a single whole. Not all physicists and philosophers accept this conclusion, and the debate over the reality of time's passage remains genuinely open. one of the deepest unresolved questions where physics and philosophy meet. Some argue that the block universe interpretation goes beyond what relativity strictly requires, that the theory describes the relationships between events without necessarily dictating that the future already exists in the same sense as the past. They point out that relativity is a theory about the structure of space-time and the relationships between events, and that it may be a mistake to read deep conclusions about the reality or unreality of time's flow directly off the mathematics. The equations describe how events relate to one another, how clocks and rulers behave, how light propagates. But whether they truly imply that the future is fixed and real, or whether they leave room for a genuine flow of time and an open future, is a matter of interpretation on which thoughtful people disagree. The mathematics of relativity is not in dispute, but its deepest meaning for the nature of time remains contested. What is not in dispute is that relativity has profoundly complicated the naive picture of time as a universal flow. Whatever the ultimate resolution, whatever the deepest truth about whether time truly passes or merely appears to, relativity has shown that the simple intuitive view cannot be the whole story. There is no universal now. Simultaneity is relative. The ordering of some events depends on the observer. Past, present, and future do not have the absolute observer-independent meaning we naturally assign to them. The river of time, flowing uniformly forward and carrying all of existence along together, is at the very least a vast oversimplification and maybe, as the block universe suggests, an illusion born of our particular perspective within an unchanging four-dimensional reality. The comfortable certainty that time simply flows, that the present is universally special, that the future does not yet exist, has been undermined at its foundations by the discoveries of relativity, leaving in its place a far stranger and more subtle picture whose full meaning we are still working to understand. Yet, even as relativity dissolves the universal present and raises the possibility that all moments exist together in an unchanging block, it leaves a profound puzzle unresolved, a puzzle that the block universe in some ways deepens rather than answers. For whatever the deepest nature of time, there is an undeniable asymmetry to our experience of it, a fundamental difference between past and future that pervades everything we know. We remember the past, but not the future. Causes precede their effects, never the reverse. A cup falls and shatters, but shattered cups do not spontaneously reassemble and leap back onto the table. Time, as we experience it, has a direction, an arrow pointing from past to future, and this directionality is among the most basic features of the world. Yet the laws of physics, including the laws of relativity, seem to draw no such distinction between past and future, working equally well in either direction. Why then does time have an arrow? Why does it flow or appear to flow only one way, from a fixed past toward an open future, when the underlying laws seem indifferent to the direction of time? This question, the puzzle of time's arrow, is among the deepest in all of physics, and it points toward aspects of time that relativity alone cannot explain. The puzzle of time's arrow begins with a strange observation about the laws of physics themselves. The fundamental laws that govern the behavior of matter and energy, including the laws of relativity and the laws governing the motions of particles, are very nearly symmetric with respect to the direction of time. What this means is that if you took any process governed by these laws and ran it backward like a film played in reverse, the reversed process would also obey the laws perfectly. The equations do not distinguish between past and future. They work equally well in both directions. A planet orbiting its star, filmed and played in reverse, would show another perfectly valid orbit, one that obeys the law of gravity just as well as the original. At the level of fundamental physics, there is no built-in arrow of time, no preferred direction, no fundamental difference between forward and backward. The laws are, to an excellent approximation, time-symmetric. And yet our experience of time is overwhelmingly asymmetric. The world we live in draws a sharp and constant distinction between past and future. We remember yesterday, but not tomorrow. We grow older, never younger. Eggs break, but do not unbreak. Heat flows from hot objects to cold ones, warming the cold and cooling the hot, never the reverse. Smoke spreads out from a fire and disperses into the air, never gathering itself back into a concentrated plume. A drop of ink released into a glass of water spreads until it colors the whole, never spontaneously collecting back into a single concentrated drop. Everywhere we look, processes run in one direction and not the other, time's arrow pointing clearly from past to future. The contrast is stark and demands an explanation. How can the world be so thoroughly asymmetric in time when the underlying laws are so nearly symmetric? Where does the arrow of time come from, if not from the fundamental laws? The answer that physics provides is subtle and profound, and it centers on a quantity called entropy, a measure of disorder, of the number of ways the components of a system can be arranged while keeping its overall appearance the same. A useful way to grasp entropy is to think about the difference between ordered and disordered arrangements. Consider a deck of cards arranged in perfect order, sorted by suit and rank. There is only one such perfectly ordered arrangement, or a very small number of them. Now consider a shuffled deck in no particular order. There are an enormous number of disordered arrangements, vastly more than the number of ordered ones. A low entropy state, like the sorted deck, is one that can be achieved in only a few ways. A high entropy state, like the shuffled deck, is one that can be achieved in a great many ways. Entropy measures, in essence, how many different detailed arrangements correspond to the same overall state, with high entropy meaning many possible arrangements and low entropy meaning few. The crucial principle, known as the second law of thermodynamics, is that the entropy of an isolated system tends to increase over time, moving from order toward disorder, from low entropy toward high. This is not a fundamental law in the same sense as the laws of motion or gravity. It is a statistical tendency, a consequence of probability, but an overwhelmingly powerful one. The reason entropy increases is simply that there are so many more disordered arrangements than ordered ones that a system, evolving and changing, is overwhelmingly likely to move toward the more numerous disordered states, simply because there are so many more of them to move into. A shuffled deck is disordered not because there is a law forbidding order, but because disorder is so much more probable, there being so many more ways to be disordered than ordered. Drop a sandcastle and it crumbles into a shapeless heap, because there are countless arrangements of sand that look like a heap and very few that look like a castle. The castle, an ordered low entropy arrangement, gives way to the heap, a disordered high entropy one, because disorder is the overwhelmingly more likely outcome. Here is the profound connection. This increase of entropy, this relentless march from order toward disorder, provides a direction to time, an arrow pointing from the past when entropy was lower toward the future when entropy is higher. The reason we can distinguish past from future, the reason time seems to flow in one direction, may be fundamentally connected to the increase of entropy. The past is the direction of lower entropy, of greater order. The future is the direction of higher entropy, of greater disorder. When we see a film of a cup shattering, we know it is running forward, because shattering increases entropy, the ordered cup giving way to disordered fragments. When we see a film of fragments assembling into a cup, we know it is running backward, because that would decrease entropy, and entropy does not spontaneously decrease. The arrow of time, the distinction between past and future that pervades all of our experience, may be nothing other than the direction in which entropy increases. Time's arrow is the arrow of growing disorder. But this explanation, illuminating as it is, raises a deeper question that pushes the puzzle back a step. If entropy tends to increase, always moving from order toward disorder, then entropy must have been lower in the past than it is now, and lower still further back, all the way to the beginning. For entropy to have been increasing throughout the entire history of the universe must have begun in a state of extraordinarily low entropy, a state of remarkable order at the moment of the Big Bang. This is a striking and puzzling requirement. The early universe, for entropy to have been increasing ever since, must have been in an exceptionally ordered, exceptionally low entropy state, far more ordered than it would be by chance. Why the universe began in such a special, ordered, low-entropy condition is one of the deep unsolved mysteries of physics, sometimes called the problem of the past hypothesis. The arrow of time, traced back to the increase of entropy, leads ultimately to the question of why the universe started in such an extraordinarily ordered state. And that question remains unanswered, pointing back to the mysterious conditions of the Big Bang itself. There is something remarkable in this chain of reasoning, this connection between the everyday experience of time's passage and the conditions of the universe at its very origin. The reason an egg breaks but does not unbreak, the reason we remember the past but not the future, the reason time seems to flow forward, traces back through the increase of entropy to the extraordinarily ordered state in which the universe began. The arrow of time that governs every moment of our lives is connected through the chain of entropy to the initial conditions of the cosmos nearly 14 billion years ago. The forward flow of time we experience in every shattering cup and every spreading drop of ink is, in this view, an inheritance from the special, ordered beginning of the universe, a legacy of the Big Bang written into every irreversible process around us. The intimacy of this connection between the most ordinary features of daily experience and the grandest cosmological questions is among the most beautiful and surprising insights in all of physics. This understanding of time's arrow, however, sits in an uneasy relationship with the block universe picture we considered earlier, and the tension between them reveals how much about time remains unresolved. If all moments exist equally in the block, past and future, together as a single unchanging four-dimensional whole, then in what sense does time flow at all? In what sense does the arrow point from past to future? The block universe seems to deny any genuine flow, any real becoming, any actual passage from past to present to future. Yet the arrow of time, the increase of entropy, the irreversibility of processes, seems to describe something real about the direction of time, something more than mere perspective. Reconciling these two pictures, the static block in which all moments coexist and the dynamic arrow that gives time its direction, is among the subtle challenges that the physics of time still faces. The arrow of time and the block universe represent two profound and partly conflicting insights into the nature of time, and their full reconciliation awaits a deeper understanding than we currently possess. And this is far from the only place where our understanding of time reaches its limits. For relativity itself, the very theory that revealed so much about time, also opens the door to possibilities stranger than the arrow or the block, possibilities that the equations permit but that strain our understanding to its breaking point.